Now, let's review what were we talking about. Okay. So what I'm going to do now is I will actually review and go over what we did about AC alternating current, and specifically I would like to talk about resonance in AC circuits today. Okay, so that's going to be important. Now, what was our definition? So I'm going to start a little bit mathematically. Our definition of a sinusoid, we said all the currents and voltages in an AC circuit can be written as a sinusoid. That can be a voltage as a function of time, or current as a function of time. And all of them, for example, in any voltage at any point in my circuit, will have three variables determining its properties. Well, we always use cosine, so let's stick with that. A cosine omega t plus phi. What was A called? It's called the amplitude. So what does that basically determine? It determines the maximum and also correspondingly the minimum value of your potential. Omega is called the angular frequency, and the period that my voltage repeats itself was 2 pi over omega, and phi is the phase. Great. Now, one thing that is quite simple is when we are solving an AC circuit, we do not really care about determining the frequency of each voltage or current, because it turns out the frequency is the same all over the circuit. Okay, you do not change that. So omega will be the same for all currents and voltages. So for each element in my circuit, I need to determine two quantities. One quantity is the amplitude, the other is the phase. Now, we've also said all these sinusoids, so A cosine omega t plus phi can be thought of as if it is the x projection of a vector. Okay, so here we're going to think of this vector as if it's rotating constantly with frequency of omega. So my theta will change as a function of time as omega t plus phi, and the length of this vector a magnitude will be just a. Okay, so for each current or voltage, instead of thinking about the sinusoid, I'm going to think of this vector in some abstract xy space. The x component here will be exactly a cosine omega t plus phi. Now, why am I doing that? Because whenever I add two functions like that, two cosines with different phases, it will be easier to just add these vectors. We are going to do standard vector addition instead of trying to actually add two cosine functions, and at the end of the day it's going to give us the correct result. All right? Okay, maybe not super clear right now, but let me go over each of my circuit elements and how they respond to an alternating current passing through them. Okay, so we've done this once, but let's do it again. I clicked on the wrong thing. Okay, so here is my resistor. I know that if a current or if a voltage V of t is V0 cosine omega t is applied to my resistor, what's the current? As you remember, resistor has no memory. It only sees what happens at the moment. So it will be V of t over R. So it's going to give me V0 over R cosine omega t. If I would like to think of this abstract vectors again, my voltage vector and my current vector are in the same direction for the resistor. Furthermore, the ratio of the lengths of these vectors, which we defined as the impedance Z, is just R. Okay? I completely understand that it doesn't make any sense to use these vectors right now. I hope by the end of this lecture it will become more clear. All right? Now, by the way, I keep saying that resistors have no memory. That, it turns out, is an important fact. And people have thought about what happens if resistors have a memory. A circuit element was theoretically defined as a memory. A circuit element was theoretically defined as a memristor. And over the last 3 years, people have actually built these elements, and there is a lot of hope that our next generation of chips may depend not on transistors but these new devices. Okay, so a resistor with a memory can do great things like doing processing. So you can look up that term and learn what that is about. This is not a memristor. Okay, so now let's talk about the capacitor. Now, if I have a capacitor, if I apply a voltage V of t, V0 cosine omega t to it, what's the current across the capacitor? What was our defining equation? I of t was C dV dt, right? C times dV dt. So it's going to be minus C times V0 times omega times sine omega t. How can I write sine omega t? I can write it as, so it's going to be minus C V0 minus omega C V0. I'm going to write it as cosine omega t. Remember, I always want to write everything as cosine plus a phase. Cosine omega t minus pi over 2. Okay? And I want to express all my voltages and currents with a positive factor in front. What I would like to do is, I would like to write omega c V0 cosine omega t plus pi over 2. Just two simple modifications to put this current into the form I like. What kind of form do I like? I like a positive amplitude and everything expressed as a cosine with some phase. Now, what does the so-called phasor diagram look like here? First of all, my voltage, if it's a vector like that, if it's at angle omega t at some time, clearly I of t is at an angle which is pi over 2 in front of that. So basically, if this is my V, my current will be leading. All of these are rotating counterclockwise. So the current is leading the voltage by pi over 2. Okay. What is the magnitude of V divided by magnitude of I? Well, V is V0 magnitude. I is omega C V0 magnitude. So this is going to be 1 over omega C. That is going to be my impedance. Now, let's do our third element, the inductor. I have plus minus. I'm applying V of t here. I'm wondering what's I of t. Now I'm going to do this a little bit different. I'll say if the current on my inductor is I0 cosine omega t, what is the voltage on it? What was the defining relation for an inductor between the current and voltage? Here, voltage was L times di dt, right? So this is going to be L times di dt. Hey, it's the same stuff again. V of t is going to be minus omega L I0 sine omega t. Or I can write all of this as omega L I0 cosine omega t plus pi over 2. Again, if I would like to think of these vectors, which are called phasors, by the way, I think it's a very good name. That's the kind of name that impresses your grandmother, right? So we use phasors today. So now be careful this time. If my current vector is at angle omega t, now it's just the opposite. Okay. The voltage vector is in front by pi over 2. Why? Cosine omega t plus pi over 2 is the voltage here. Okay. So V leads I here, and here I leads V. How about the impedance? How about if I look at the ratios here? Omega L I0 divided by I0. So the impedance is omega times L. Now, it's kind of interesting. What happens here is that the resistance, the effective resistance we defined as impedance of a capacitor goes down with increasing frequency, while for an inductor, if you are at high frequencies, it acts more and more like a resistor. All right? Good. Now, how do these help us solve any circuit? Let's start with something simple. Let's say that I have an AC voltage source, a resistor, and a capacitor. Let's say that this voltage source has voltage V0 cosine omega t. All right? Now I would like to calculate two things. First, I would like to find out what is I of t. Second, I would like to calculate, find the average power dissipated in the resistor. Okay? Now, how do we do this? First of all, what are my defining equations here? Let's think about it. Here, I'll have some voltage across the resistor, and here I'll have a voltage across the capacitor. And these must add up to V of t, right? So what I basically say is that V of t must be V resistor of t plus V capacitor of t. Good. The nice thing is that all these three elements share the same current, right? It's the same current they actually share. There's only one current going through my loop. So if I think of this phasor diagram, let's say that this is my current vector. It's passing through all of my elements. As a vector, can you tell me what is VR vector? What's the direction of the VR vector compared to the direction of the current? It must be the same, because VR vector must be just R times I vector. So let me do this in another color. So here will be my VR vector, okay, which will be, so VR magnitude will be R times I, whatever is passing through my loop. How about the voltage across the capacitor though? Voltage across the capacitor. Okay. First of all, which direction was the voltage across a capacitor? The voltage across a capacitor is lagging behind the current. Okay? So the current is 90 degrees in front of my voltage. So which direction do I have the voltage of the capacitor? It will be like this. Okay? So this is going to be the voltage of the capacitor. It's lagging 90 degrees behind the current. How about the magnitude of VC? Well, what was the impedance for a capacitor? The ratio of voltage to current? It was 1 over omega C. So it must be 1 over omega C times I. That is great. Now, can you tell me what is the total voltage or the source voltage here? The source voltage, we said V is VR plus VC. So V of t must be VC plus VR. Or if I think of the diagrams, what do I need to do? I need to add these two vectors, VR vector and VC vector. So I'm going to do that. I'm going to add them. This is going to be V of t. Okay. So can you tell me V of t magnitude? What's the V of t magnitude? Because the angle here is 90 degrees, it must be square root of VC square plus VR square. Did I find both of them? Yes, I did. So this is going to be r square I square plus 1 over omega square c square times I square. So this is going to be r square plus 1 over omega c square times I. Or in other words, I actually found the amplitude of the current running through my circuit. What's the amplitude of the current running through my circuit? It's going to be apparently V0 divided by square root of r square plus 1 over omega square c square. But is that enough? I found the maximum of the current. I also need the phase of the current, right? What is that phase? I've said V0 is cosine omega t. So basically the angle of this V, total voltage, or the source voltage, the angle from 0 to here is omega t. So what I need to find out is the phase. My current is in front of my voltage, apparently. And what is the tangent of that angle? It's going to be Vc divided by Vr. What is Vc? 1 over omega c times I. What's Vr? R times I. So it's going to be 1 over omega c R. So now I can write the current as a function of time. It's going to be V0 divided by this R square, 1 over omega square C square times cosine omega t plus phi, where phi is apparently arctangent 1 over omega RC. So I have found both the angle and the amplitude of the current running through my circuit. Now, how about, that was only part of the question. The next part of the question was, how much power is dissipated on my resistor? Right? That was the other thing I need to calculate. Now, this is kind of an interesting question, because what is the power at any time of my circuit? It's always going to be whatever, and the only thing that dissipates power is the resistor. So this is going to be VR of t times I of t, or if you want, R square times I of t. Right. Good. At least one person is listening. I square times R of t. Now, this is kind of interesting. So this actually tells me is R times, let me just call this I0, okay? So it's going to be R times I0 square times cosine square omega t plus phi. So if I look at the power dissipated as a function of time on my resistor, it's not a constant value. So it's apparently it's going to be some function like this, right? Cosine square. Cosine square never goes to. The maximum value is R times I0 square. Now, look at the lamps here. The light coming out of a lamp is pretty much a dissipation mechanism, right? Is that light oscillating? Well, I mean, it depends on what kind of lamp we have, but especially these fluorescent lights, they are oscillating, okay? But the oscillation frequency is very high. 50 Hertz or 60 Hertz. Actually, it's probably twice that there, okay? So when this oscillation is happening so fast, we are not really interested in what's going on at a moment in time. We are more interested in, on the average, how much light is coming out of my lamp. Or if I have a heater, I'm not interested in whether it's heating and cooling at 50 times every second. I'm more interested in how much heat it will give me if I wait there for 10 minutes, right? So what I'm interested in is the average value of this power. How can I calculate the average power? Now, this thing is periodic, right? If it's periodic, I think the best way to do it is integrate the power over one period and divide by a period, okay? Because it's going to repeat itself. That's a good way to average. And what will the average value be? We can immediately see from this diagram. Okay, first let me write this down. It's going to be 1 over t times 0 to t. P of t, we said, is I0 square times r times cosine square omega t plus phi dt. So let me take these out. R I0 squared over t. Now, cosine square, I'm going to write it a little bit differently. Cosine square theta is 1/2 cosine 2 theta, right? Yes. Plus 1. Okay? Everyone agrees with me? I'm not doing anything wrong? Good. Now, so this integral is actually not too hard. I take 1/2 out. I'm going to say it's cosine 2 omega t plus phi plus 1 times dt from 0 to the period. Plus 2 pi? Phi. Plus 2 phi. Yes, thank you. Okay, now I have two separate integrals. Let me r I0 square over 2. 1 over t. What's the integral of cosine? It's sine. So it's going to be 1 over 2 omega sine 2 omega t plus 2 phi at 0 and t. That's one term. And the other term is just, I have 1 over t, and here I have t at 0 and t. It's the simplest integral in the world again. So this thing gives me 1. How about this though? It will give me two things. Do we remember what t was in terms of omega? It's 2 pi over omega, right? So what do I have here? I have 1 over 4 pi. In the upper limit, I have sine 2 times omega times 2 pi over omega plus phi minus at 0 sine phi. Omegas cancel. What is phi plus 4 pi of the sine of that? It's again sine phi. So these two canceled. This whole term is 0. So apparently the average power is r times I0 square divided by 2. Aha. So, I mean, whenever I have an alternating current, the power is determined not by the peak values of the current, apparently, but it's peak square over 2, or people, for engineers, for some reason, define something called IRMS, which is I0, the peak, divided by square root of 2. RMS means root mean square. So the average power is going to be I square RMS. Okay, so this 1/2 factor we have to keep in mind when we are dealing with alternating current. Actually, the voltage in our outlets is 220 volts RMS. Okay, not the peak. Good. Now comes another circuit. Let me put a capacitor C, an inductor L, and then resistor R, and tie all of them to V of t, which is V0 cosine omega t. Okay. Now, once again, I would like to find out two things. First, I would like to find out the current here, and the second thing is I would like to find out the voltage here. And just as I did previously, I'm going to do the following. I will solve this using these phasor diagrams. All three elements in this circuit share the same current, right? So here's what I will do. I'll say that I have some current vector I. Now, what is the VR vector direction? It's the same direction with the current, right? So my VR vector will be here, and VR magnitude will be R times I0, the peak current. Okay? How about VC? The direction of VC for the, let's go back to our definition. For the capacitor, voltage is behind the current. So VC will be in this direction. How about VL? And VC magnitude is going to be 1 over omega c times I0. How about VL, the direction? We have found it was just the opposite. Now voltage is leading the current for an inductor. So the voltage is going to be that direction. VL magnitude is omega L times I0. Now, how do I find the total voltage vector? It's going to be the sum of these three vectors. Okay. So I can maybe try to sum up all these three. Let's assume for a moment VL is larger than VC. So I will actually have something like this. VC here. And their sum will be something like this, right? This is going to be my V. What is the magnitude of V? The magnitude of V, now what's the magnitude of, we have to look at the magnitude in two sides. On one side, magnitude is VR. On the other side, magnitude is VL minus VC magnitude. So it's going to be R square I square plus omega L minus 1 over omega C squared I squared. Or if I just, and this magnitude must be equal to V0, so I magnitude must be V0 divided by R square plus omega L minus 1 over omega C squared. How about the phase angle now? Well, where is that phase angle? This phase angle is going to be, the phase angle is between the total voltage and the total current, right? So that's going to be my phase angle. Or if I think I'm going to redraw that triangle again, one side is 1 over omega L minus 1 over omega C. The other side is R. And when I add them, I get the phase angle phi. So phi is apparently arctangent omega L minus 1 over omega C divided by R. Now, can I look at the power dissipated here? The power dissipated in the circuit is again going to be R times I0 squared divided by 2. It's the same calculation for any cosine. So it's actually going to be R times V0 squared divided by 2 R squared plus omega L minus 1 over omega C squared. At which frequency is the dissipated power maximum? Look at this formula. I have R square, V0 square, I cannot change these. 2 R square, I cannot change. When I change my frequency, the only factor it actually changes is here. And it's an absolute value square. So the maximum power is when I have minimum of this term. When omega L is equal to 1 over C. Right? Clearly, omega L is equal to 1 over omega. Wow! So, at what we call omega 0, 1 over square root of LC, power is maximum. Actually, I can do the following. I can plot power as a function of frequency here. This function basically. What we will find is that it's a narrow peak around omega 0. width of that peak is more or less R over L actually. So if I have very little resistance, I'll actually have a much narrower peak. Okay. And now why is this important? This turns out it's extremely important. This is called resonance. Now why is this important? Here is my L, C, and R. Now, you actually use this circuit all the time. Let's not think of a real AC source like our outlet there, power outlet. But think of an antenna. When I have an antenna, so it drives a circuit. And onto my antenna, a lot of electromagnetic waves come. At the same time, Bilkent radio's frequency is coming here. Power FM's frequency is coming here. Radio ODTÜ frequency is coming here. Aşk FM Ankara havaları is coming here. Okay. Now, at the other end, over the resistor, this resistor is actually inside my headphone. Okay. I want to listen to Bilkent radio, not Aşk FM. Okay. What do I want? I actually want the following. If this is the frequency of Bilkent radio, it drives a lot of current. I hear all that frequencies. But if this is Aşk FM, it's not driving much current. Okay? So I don't hear that at all. It's all suppressed. So I've changed my mind. I don't want to listen to Bilkent radio anymore. I want to listen to Aşk FM. What do? I change the values of C or L so that now my resonance frequency is shifted to Aşk FM's frequency. So that's what you do by tuning your radio. All right. Now, no modern radio is this simple. There is a lot of more sophisticated things going on inside the real radio. But that was the basic idea. And when radios were first commercially available, probably for your grandmothers, grandfathers, they bought a radio and it was a signal. When the first radios, which were not really sold in Turkey, they were just a box. They had only one frequency. If you wanted to tune to another frequency, you called some other guy. He came in and adjusted the screw inside, which changed the value of the capacitor. Okay. Then someone said, hey, why don't I put in a dial, which will change the number, well, the area of the capacitor, which will change capacitance. So you can change until you hear another frequency. Okay. So that was what they were doing in the old days. There was a big dial. When you dialed it, it really rotated two plates with respect to each other, changed the capacitance, so it changed the resonant frequency. Now, I've talked as if this resonance is something great. It allows us to listen to whatever radio station we want. But it also has a darker side. Now, see what happens. Let's say that I have a very small resistance in the circuit. If I have very small resistance, you would expect the power to be also very small. Not much resistance there. However, if I'm exactly on resonance, if I'm the peak point here, the peak power, I'm just writing from here R V0 square, R times V0 square divided by 2R square. So they cancel. So the peak power is V0 square over 2R. And if you have very small resistance, you actually get the opposite of what you expected. you get huge amount of power. Suddenly your radio is acting like a heater, right? I mean, you put in a very small resistance there, but it's getting a lot of current. Obviously, I mean, in a radio that's not a problem, but people design things so as there is not much dissipated power. You don't want to generate too much heat or other unwanted effects. When you build a bridge, you don't want too much oscillations on that bridge. And you design it so that when cars pass through that bridge, they create some waves, but they are not resonant. They do not actually shake the bridge. It turns out, just 2 years ago, in the Bosphorus Marathon, a lot of people came onto Boğaziçi Bridge. People were walking on the bridge. And the bridge was not designed for that. It started swaying. It was really, because of all these different frequencies people were pumping in, some of them were creating a resonance with the main mode of the bridge. And God forbid, it could be possible that they could break the bridge. Such things have happened. Okay? So resonance is something that needs to be controlled very well. It can be put to good use, but it can also have catastrophic consequences. And it's not just circuits, it's all kinds of mechanical systems. Anytime you have an oscillator, anything that oscillates, when you try to drive it, the natural frequency, what was that omega 0? It was the oscillation frequency of my LC circuit. So if I leave the system by itself, that would be the frequency it oscillates. So anytime you want to get a lot of response from a system, you try to drive it at its natural frequency. That's also true for a swing. If you want to get, if you want to push your, well, not daughter or son, for your nieces higher and higher, you need to push them exactly at the swinging frequency. And that's what you do once you give one push at each swing. Okay? So that's all I actually want to tell you about AC circuits. We're going to solve some more examples. On Monday we'll have 2 quizzes. Don't worry. Don't forget about that. I'll see you on Monday then.